Alright, so in this tutorial we are going to derive the equation for centripetal acceleration. We learned in the last tutorial that centripetal acceleration, A sub c, is v squared over r. And we want to show where that comes from by looking at a representative circle and doing some geometry and algebra with it. Before we get into the details, I want you to understand the big picture is that this equation, v squared over r, really comes from the definition of acceleration, which is change in velocity over time. So what we're going to show through some clever mathematics is how this equation can be transformed to this equation when we are moving in a circle at a constant speed. And that constant speed part is important for the derivation, but we don't always have to have constant speed when we apply this. Alright, so let's take a look at our reference circle and some concepts therein, lay the foundation before we do the derivation. So we're going to move it, imagine an object moving in a partial circle of radius r, right here, okay, at a constant speed, okay. In time t, it goes from position A right here to position B, and it covers the displacement x, that little arc length there. Alright, and then we know it has speed, so we're going to label the speeds. I'm going to label it u for this one right here, so the u vector, and at position B, its velocity or speed is v. Okay? Now, we've already said that u and v are the same speed, but since they're vectors, they're going to be, they're pointing in different directions, so their velocities are different even though the speeds are the same. All right, so to calculate the acceleration, we use the definition right over here, A equals delta v all over t. Note that it's change in velocity rather than initial or final. So, this might seem simple enough, but let's look at the delta v part. Let's say that u was 10 meters per second and v was 10 meters per second. And so we want to calculate the acceleration. You might be tempted to say, well, 10 minus 10 is 0, therefore the acceleration is 0. However, that would be wrong because we're subtracting vectors. And you can't say 10 to the right is the same as 10 to the down and to the right. So when they subtract them, we won't get 0. So this requires a little bit of massaging, if you will, to understand the delta v part. So that's where our main focus is going to be. So in this next bullet, in order to find delta v, we're going to use vector subtraction. Okay? And as I just said, even though the absolute values of v and u, which is another words of saying their speeds, are this, their difference isn't 0 because of the different directions. Okay, so again, 10 minus 10 meters per second minus 10 meters per second is not necessarily 0 if the vectors are in different directions. Alright, so I'll come back up to the last bullet in a second, so let me just zoom this up. Alright, so here's what we have. We want to find the acceleration by going from position A to position B, noting that our velocity has changed by virtue of changing direction. So what I'm going to do is pick up, if you will, these two vectors, vector u and vector v, and place them right over here. So this would be vector u, and this would be vector v. All right, we just transplant them and we put them tail to tail, okay, to indicate the change in the velocities. So we want to represent a vector that is delta v. Well, delta v is nothing more than my final minus my initial, right, by definition. So I want to show the vector that represents v minus u. Well, v minus u, as we learned a while ago, is the same as v plus a negative u. So if I want to represent it, I would take the negative u, or u, and make it negative by turning the arrow around that way. Okay, so my arrowhead isn't very well lined up. And so if this is the beginning of negative u, and here is the end of v, then my vector from here to here is delta v. Okay? So look at that again. Convince yourself that you can do that, because it's a very important process that we've learned, how to take two vectors and find the difference between them. And here we see the difference is really just a change in one or the other. So there's a lot of significance to that. So what I want you to notice is that in this vector triangle of u, v, and delta v, we have an angle. I'm going to rewrite it as theta. Okay, what does that theta represent? That represents how much angle the object has moved in this circle right here. So in other words, this theta, as we go from the vertical position, if you will, the 12 o'clock position to the, let's say, 1 o'clock position, is the same angle we see in our vector triangle over here. So what can we say about that? This is an important thing about geometry. If I look at this triangle right here, so I'm going to draw a triangle. I have r, theta, r, right? I want you to notice that that has to be similar to triangle, my vector triangle of u, theta, v. Okay? And that's really the crux to this derivation. And the reason I'm justifying this, remember in geometry, we have side angle side. In other words, r and r are the same, and u and v are the same. Remember, they're the same speeds, okay, in terms of their magnitude, and they share a common angle in terms of theta. So what can I do with that? Well, I can do something very clever. If you remember something about similar triangles, we know that we can do proportions with them. So what I can say is this v divided by this delta v. So why don't we do that right over here? We can say v divided by delta v must equal the corresponding parts to our triangle within the circle right here. So delta, or v, corresponds to r all over x. Okay, so if we solve for delta v, because that's what we're really interested in to help us find acceleration, then we can say delta v, if we do a little rearranging, cross multiplying, is v times x all over r. Okay, so give yourself a chance to recognize why that would change from this proportionality to this equation. Okay, now here's where something is really cool. Let's look at this distance traveled x. Okay, so x is drawn in this triangle as a straight line when it technically, and I know I've overwhelmed it with my marker here, but let me erase it a little bit, is really an arc. Okay, so let me draw x from point to point, and notice that the arc length is a little bit different than the actual line there. However, if, this is a really important if theta, the angle we move, is really small, in other words, it's less than a degree, which corresponds to a tiny amount of time, we can say that x is going to be nothing more than how fast we're moving multiplied by the time that we moved. Okay? Remember, we're moving at a constant speed, so as we go from A to B along this line, and it will be very close to a line when our theta is really, really small, then that distance is vt. So we can substitute it into our equation above, and we can say delta v equals, okay, our original v times t all over r. Okay, so there's my substitution in for x. All right. What does that give us? It gives us, no, actually, before I do anything else, we can one more step. Let's move the t to the other side, and we can say delta v all over t is equal to v times v squared all over r. And what is delta v over t? Well, it's nothing more than our centripetal acceleration. So that's how we derive the acceleration of an object moving in an arc or a circle. Okay, the beauty of this equation is we don't have to worry about the time over which we're accelerating, because in essence it doesn't matter whether we're accelerating for a brief period of time or for the whole period. The value of the acceleration, a, is going to be the same regardless. So it makes sense that we would express our acceleration without time in it, because it's really independent of time. What it really depends on is how curved our circle is, in other words the radius, and how fast that we're changing. So the faster you change your direction, the greater the acceleration. And in fact, we see that how fast we change it, acceleration goes by the square of how fast we change it. All right, so make sure you look over the key elements of this derivation so that you understand each part. You're not necessarily expected to replicate it as a whole, but you should understand where each part comes from.